welcome to lecture number 14 of electronic devices and circuits. In this video we will do gate questions on BJT and FET. Now one thing I want to tell you that in terms of EDC, very simple problems, mostly the theoretical ones are considered for EDC, and rest of them, which are the complex numerical problems, or the data questions in which you are given a large amount of data and then linked questions are asked, they all will come under analog electronics, because there you are doing a deep study of the BJT as well as FET in terms of the operation, in terms of the biasing, in terms of the, in that analog you have studied about the BJT amplifiers also, and the FET amplifiers and their characteristics, their input characteristics, drain characteristics, transfer characteristics and whatnot. But here we study it as a device, right? So that's what I wanted to tell you. So let's get started. Now this question says that which of the following effects can be caused by rise in the temperature. First option is increase in MOSFET current, second option is increase in BJT current, third is decrease in MOSFET current, and D is decrease in the BJT current. And now we know that IC is equals to beta IB plus 1 plus beta ICBO, and in some cases they write just ICO. So yes, we know that as the temperature increases, the mobility decreases. I told you in the earlier lectures of this playlist of this EDC videos. So what we can say, that in MOSFET, as the temperature increases, our MOSFET current, what is our MOSFET current? IDS, it decreases. Now let's talk about our BJT. Yes, I wrote this formula over here. So we know that this current is dependent entirely on the temperature. So as the temperature increases, this current increases. As a result of this current increases. Right or wrong? So can I take this from this, and from this is case number 1 and this is case number 2. From this I can take this. So both B and C are correct. A BJT is said to be operating in the saturation region if we know that both the junction, which junction, JE and JC, both are forward bias, right? This was the table, so the answer is D. The reverse saturation current of the collector base junction ICBO of a BJT is found to be 10 nanoamperes at low collector voltages. The low current amplification factor alpha is 0.98. Find out the change in collector current with its base open ICEO when the collector voltage is increased such that the alpha is increased by 1%. So we know this formula. Which formula? That ICEO is equals to beta plus 1 ICBO. Now what is given? Alpha is given, and here what it is? Beta. So how can I calculate it? I told you. So this will come out to be, if I put 0.98, it will come out to be 49. Now I am putting it in equation 1. What do I get by putting in equation 1? That my ICO is equal to, what is this? 49 plus 1 is 50 into 10 nanoamperes. This is equal to 500 nanoamperes. Till now it is clear. Now this is at alpha is equals to 0.98, but what we are doing, we are increasing this by 1%, right? So what will be the alpha dash? The alpha new, the new alpha, which is increased by 0.98%, so it will be 0.01 into what? 0.98. What is this? this will be 0.9898. Now let's calculate beta for this. This will be this dash 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 alpha dash over 1 minus alpha dash. So this will come out to be 97. Now let's calculate ICEO dash. ICEO dash will be 97 plus 1 is 98. I'm putting in equation number 1 into this will be 980 nanoampere. But what it is asking? It is asking us find out the change in collector current. So the change will be given as percentage change will be given as the new one minus the old one upon the old one into 100. This will be 480, right? So the answer will be 96%. Answer is 96%. In a BJT at room temperature, if the emitter current is doubled, then the voltage across its base emitter junction, then we have 4 options: doubles, halves, increases by 20 millivolt, decreases by about 20 millivolt. So we know this formula. Which formula? We know about this formula from our PN junction diode lecture, and as well as while solving the gate questions I told you about this formula. This is IF in that, right? But here what is happening, it is asking about the emitter current, so it will act like our PN junction only. We can consider it as our PN junction only. Why? Because in the active region what we are doing, we are forward biasing it, right? So I can write, instead of IF, I can write it IE. Both are same because we are considering here it as PN junction. Why? Because we are considering the emitter current. Now we know this, and in those questions I told you so many times that how we now from this I can write it like this, and ln I over I naught. This is E and this is T. I told you that how we come over here. If you are not able to recall it, I would recommend you to watch the previous year gate questions. I have done it in 2 parts for the PN junction diodes. In that I have done it, and you can always just turn the pages of your copy. I hope you have written it. So I'm not doing it. I don't want to waste time in how I got this, because that time I did it in 2 to 3 questions. Okay, so now what? Now this is what is originally happening. Now what it is saying? It is saying that the emitter current is doubled. So can I write it like this? That the emitter current is doubled means it is this. Obviously, suppose this is my equation 1, this is my equation 2, and I'm taking the original one as V1 and this is V2. So what I am doing, I will now subtract 2 from 1. So what will I get? I will get V2 minus V1 is equals to Vt, and this will cancel. This is in division, so I'll get this, right? Clear till here? Now it is saying that it is at room temperature, so I'll take this as 0.026 into what is this? I hope that you are using your gate calculators. There is an app for it which is available on store, so you should download it. So what we will get after solving this? 18 millivolt, which is approximately equal to this. So the answer is C. Now you may ask me that, ma'am, why you have not considered this eta? So we know that for germanium it is 1, but for silicon it is 2, right? But for the question's sake, I am taking it 1 only, so that our calculation become easier. And of course, what happens at the higher frequency, that this eta is 1 for silicon also, so that's why I'm considering it as 1, and I haven't considered it over here. in the denominator. Okay. The early effect in a bipolar junction transistor is caused by, I told you about the early effect. What was happening in the early effect? I told you that in how can we explain it? It is the process where, yes, tell me, it is the process where the effective base width of the transistor is altered by varying the collector junction voltage, which is in the reverse bias, right? So what is happening in the transistor? That we are, by changing the collector junction voltage, the base width, the effective base width of the transistor is decreased, and this is called as the early effect. The impurity commonly used for realizing the base region of the silicon NPN transistor is now boron. It's boron. It is the most common trivalent impurity which is used to realize a NPN transistor base region. Consider the following statements. Statement number 1 says the beta of the BJT reduces if the base width is increased, and second statement says the beta of the BJT increases if the doping concentration in the base is increased, and we have to tell that which one is false and which one is true. Now, one thing you should know, that if the recombination in the base region will increase, then the alpha will decrease, and it is saying that beta of the BJT reduces if the base width, so it is saying that the base width is increased. If the base width is increased, it means that the recombination in the base will increase, which means that the beta will decrease, and due to which alpha will decrease. I'm so sorry, alpha will decrease, and due to which our beta will also decrease. Why beta will decrease? Because beta is equal to alpha 1 minus alpha, isn't it? So our beta will decrease. Why it is decreasing? Because base width is increasing, due to which the recombination in the base region will increase, due to which our alpha will decrease, due to which our beta will decrease. Now, what is the second statement saying? That they are increasing the doping concentration. So if I am increasing the doping concentration, what will happen? The recombination in the base region will increase again, of course, because it will have high number of holes. So high number of holes will recombine with the electrons which are coming from the emitter side. So the recombination in the base region will increase, due to which our alpha will decrease, due to which our beta will decrease. Why? Because beta is equals to alpha 1 minus alpha, which we derived. So this is wrong, because beta will not increase, it will decrease. So this is wrong and this is right. So the answer is D. Now this question is being again asked in 2006 on early effect. The phenomenon known as early effect in BJT refers to the reduction of effective base width. Now you know the answer. Please pause the video and take the answer, because if you will not take the answer, I'll come there and I'll beat you hard. Okay, so please take the answer. What is the answer? The answer is B. For a BJT, the common base current gain alpha is equal to 0.98 and the collector base junction reverse bias saturation current ICO is equals to 0.6 microamperes. This BJT is connected in common emitter mode, okay, and operated in the active region, okay, with a base current. The base current is given 20 microampere, the collector current for this mode of operation. So it's so simple. We know that IC is equals to beta IB plus 1 plus beta ICO, right, or ICBO, whatever. Here ICO is given. So what we have, alpha or beta? We have alpha. We have alpha is equals to 0.98. So quickly tell me what will be the beta. What is the formula? The formula is this. So I am putting it like this. Solve it before me. Solve it before me. Solve this question and put the value. This will be, am I correct? This will be 49, and I'm putting the value over here. This will be 49. This will be 20. Solve it before me. This will be 50. ICO is 0.6. Is your answer 1.01 milliampere? Congratulations, you are my favorite student. The answer is D. The pinch off voltage for an N channel JFET is 4 volt. Then pinch off occurs for VDS when VGS is equals to minus 1 volt is. So what is given? VP is given. What is the value? 4 volt, right? What else is given? VGS is given. What is the value of it? 1 volt, right? Minus 1 it is, right? So I don't know, it's in my one book it is a misprint or what, because in my book it is written -1. I don't know if the value is 1 or not. So either way, the formula is, I am writing a mod over here, and so that the minus sign is absorbed. So this is the formula. So what will be the pinch off? Where will be the pinch off? Occurs for VDS when VGS is -1. This will be 3 volts. So easy. A. The pinch off voltage of a JFET is 5 volt. Its cutoff voltage is, and options were given something like this. This was, and B and C 2.5. This is 0. And D it is, I wanted to take the answer because we know it, that our pinch off voltage is the other name of cutoff voltage only. If you've seen the graph, our pinch off voltage is our cutoff voltage. It's just a matter of characteristics. In the characteristics, if you'll see, the both they overlap each other. So the answer is B. And N channel JFET has IDSS as 1 milliampere, and VP, the pinch off voltage, is -5 volt. Its maximum transconductance is. So this is the formula for transconductance, where this GM0 is the maximum transconductance. And what is the maximum transconductance? It is the transconductance which is defined at VGS is equals to 0. So if it is 0, what will happen? This will be 1. So this will be the maximum one. So all the other GM which we are calculating, they will be less than this maximum transconductance. Till now it is clear. Now this GM0 is given by IDSS. You should remember this, and it is the mod of pinch off voltage. Why? Because this cannot be negative, so we just have to put the values. Yes, and here we have a 2 also. I'm sorry, I skipped it. Yes, so it is 1 milliampere into 2. So this will be 2, and this will be 5, and this will be 0.4 milliampere per volt. This is an important formula which I want you to note it down in your notebook. This is the formula for maximum transconductance, and subsequently this formula also. So do write it in your notebook. So yes, only these kind of questions will come. You have to just put the values in the equation, in the formulas which I told you, whether it is drain current, whether it is emitter current, whether it is this transconductance, or it might be the amplification factor, or they might give you some values, and they'll tell you to calculate the junction capacitance or the storage capacitance, whatever be, you should remember the formulas. That is very very important. And rest all, if something is related to circuits etc, that I hope, I wish that you have learned it in analog. So that's it, that's all for this video. In the next video we will be doing the IC fabrication process. Make sure that you see it, because I will be doing it in a very very simplified way, the most simplified way. I'm doing my homework on that, and I'll try to give you a very simple video on it, so that you know you can retain it in the exam. We'll learn about etching, masking, photolithography, and what not, metallization, what is happening, what is substrate and all. So see you in the next video. Bye.